All right, another form of proof that you should have looked at this week is proof by contradiction. And I want to do an example of that as well. I don't know why I just did that. So we're going to prove that the square root of 2 is an irrational number. And we're going to do that by contradiction. Now, to say that something is irrational is to say that there does not exist a rational number that has that property, in this case of being the square root of 2. And in general, I would say it's at least an even bet, and maybe more, that whenever you're asked to prove that something doesn't exist, that proof by contradiction is one of the first things you should think of. Assume that it does and show that that leads to some kind of nonsense result. So to prove that square root of 2 is irrational, we will instead assume, by way of contradiction, that the square root of 2 is rational. Now, what does it mean to be rational? It means that I can write that number as one integer divided by another integer. In fact, even a little bit stronger. If square root of 2 is irrational, then I am saying that the square root of 2 can be written as m over n, where m and n are integers, and they have no common factors other than 1. Because, if, for example, I wanted to make the argument that 1.5 is a rational number, I can write that as 3/2, or I can write it as 6/4, or I can write it as 9/6. But all of those are not the simplest form of the fraction. I get to the simplest form of the fraction, 3 over 2, by taking out any common factors. So if the square root of 2 were rational, I should be able to write it as a simplified fraction. What's more, I can sort of rule out the possibility that n could be 1. Because if n could be 1, then I'd have m divided by 1, which means that I'd be saying that the square root of 2 is an integer. So let's rule that possibility out first. And I can do that by simply enumerating each of the integers up to 2 and saying, are you the square root of 2? Well, 0 squared is not 2, so 0 is not the square root of 2. 1 squared is not 2, so 1 is not the square root of 2. 2 squared is not 2, so 2 is not the square root of 2. And we know the square root can't be larger than the integer that you're taking the square root of. So that's as far as we need to go. So we can actually claim with some justification that n must be greater than 1 and rule out the integer case. All right, so now how do we turn this into a contradiction? Well, if square root of 2 equals m over n, I can square both sides of that equation and say that that means that 2 equals, let's see, I have m on top, m squared over n squared. And then, since we've already established that n has to be greater than 1, we don't have to worry about the possibility that 0, that's lucky. That means I can multiply through by n squared on both sides and say that 2n squared equals m squared. And what does that tell us? Well, it tells us that, in fact, m squared must be an even number, which we know means, from our last proof, or its corollary, that m must be an even number as well. So keep that in mind. M is an even number. Now, if m is an even number, then there is some k for which m equals 2k. And that means that I can write the 2n squared, which we've already established is equal to m squared, is also equal to 2k squared, which is equal to 4k squared. You can, of course, not hear the parentheses when I'm speaking this out loud. So what does that tell me? Well, if I divide the leftmost and the rightmost in that chain by 2, I'm left with n squared equals 2k squared. And that means that n squared must be an even number, which means that n is an even number. So now we've established that both n and m are even numbers, which means both of them are evenly divisible by 2. And that contradicts our assumption that we made earlier, that we had chosen m and m. They have no common factors other than 1. So we have a contradiction, which means that our initial assumption that we can write square root of 2 in that form, m over n, cannot be supported. We have to assume that that is false, and therefore 2 cannot be written, square root of 2 cannot be written as a rational number. Now, if you want to know where this proof would fall down with something where the square root is rational, it falls down on that step of saying that when we start trying to take the square, that n would have to be greater than 1. If I were to try to do the same thing to prove that the square root of 4 is an irrational number, it would fall down because 4, when I write it out as a rational form, I'm eventually going to have to put it over 1, as its square root is 2 over 1. And so that step of enumerating all the integers would have failed for us there.